Hello everyone. The next electrophilic substitution reaction after nitration of phenol is halogenation of phenol. Halogenation means add of halogens group on the benzene ring of phenol like fluorine, chlorine, bromine, iodine. That's why halogenation is of four types: fluorination, chlorination, bromination, iodination. Only bromination is in the syllabus of 12th, JEE, NEET and BSc. Let's discuss what are the important points in bromination. For the bromination of phenol, we need to react our phenol. This is our phenol molecule. As you know, these two positions are ortho. These are meta positions and this is para position. We need to react phenol with bromine. Bromine is a reddish brown liquid. Now when you will bring this reaction in the presence of water as a solvent, obviously we know this is electrophilic substitution reaction. The brominium ion as an electrophile will prefer to attack on which position? Ortho and para position. In the presence of water as a solvent, all the three positions will be occupied simultaneously. Two ortho positions and one para position. Means tri-substitution will happen. Three hydrogens will be substituted by bromine. Side product will be HBr. I will balance the equation when I will solve the mechanism. This product which is generated, IUPAC naming will be 2,4,6 tribromo phenol. As numbering will start from here. This is main functional group, one number to it. Side chains will get higher number. 2, 4, 6 positions are occupied by bromine, so 2, 4, 6 tribromo phenol. If I talk about its physical appearance, so it's a white precipitate. As you know, precipitates are insoluble particles which will settle down in a test tube during reaction. So this is the reaction when phenol reacts with bromine in the presence of water as a solvent. This product will be generated as a white precipitate. Now, the same bromination if you are doing in the presence of CS2, carbon disulfide, or CCl4, carbon tetrachloride as a solvent. Bromination will happen, but it will be mono-substituted bromination. Means at one time, only one bromine will be added on a phenol. And obviously which position? Ortho and para. Only one hydrogen is replaced by bromine, either from ortho or from para. So ortho substituted product, para substituted products will generate simultaneously or like this, separately. Ortho separate, para separate. But here you can check ortho and para substitution was happening on a same ring. This is orthobromophenol, or you can call it 2-bromophenol, because the position is 1, 2, or 2-bromophenol. Here 1, 2, 3, 4, it will be 4-bromophenol, or common name para-bromophenol. Out of these two, it will be major, reason already we have discussed many a time, and it will be minor. So this difference will be created by our solvents. If water is a solvent, you can check tri-substitution will happen, and if CS2, CCl4 as a solvent, we will have a mono-substitution and product will be these. Let's check what is the reason behind it. Very, very important. To understand this concept, first we need to answer this question. This is phenol. and this is phenoxide ion. Phenoxide ion, and this is phenol. We know how phenol can create phenoxide ion. When phenol will release H positive and these electrons will transfer toward oxygen, H positive will release out, the phenol will become phenoxide ion. Now the question is, which benzene ring have more electron density? Phenol benzene ring have more electron density or phenoxide ion ring have more electron density? Answer is this one. Phenoxide ion benzene ring will have more electron density as compared to phenol. To understand the concept, this concept must be clear. The benzene ring of which will have more electronic density means more amount of electron. Phenol benzene ring or phenoxide? The answer is phenoxide benzene ring will have more electronic density. Reason? Let's check. For its reason, you need to draw their resonance. This is phenol. As you know, this benzene ring is getting electrons due to resonance like this. Lone pair of oxygen will come here. Pi electrons will shift here. I will not discuss it again. Many a time we have discussed. Directly I am going to draw it. This is the resonance of phenol. Due to this resonance, you can check benzene ring is occupying extra electrons on which positions? Ortho, para, ortho. Now if I draw the resonance of phenoxide ion, same way, now on this oxygen positive charge will not come because the negative charge already it have due to extra electron, and when it has shifted these two electrons here, one electron has completely transferred toward carbon, so its negative charge will finish. In phenoxide ion, you can also check electrons are coming on ortho and para positions. So benzene ring will have higher electron density on ortho and para position. This is the complete resonance of phenoxide ion. Now, which benzene ring will have higher electronic density? The answer is phenoxide ion one. Why? The reason is very obvious. Check. First check the oxygen of phenol. When oxygen of phenol is delivering its electron in a ring during resonance, positive charge it is occupying. And you can check that positive charge is all the time on it. Only these two structures, oxygen, do not have a positive charge, but rest all structures, oxygen have a positive charge. Oxygen with positive charge is highly unstable, as we know. Means this oxygen is feeling very difficulty to donate its electron during resonance, because after donation of electron in the resonance, it is occupying what charge? Positive charge. Means instability. Whereas the oxygen of phenoxide, you can check, it was unstable, and after donating electron in the benzene ring, it is getting stability. Here it do not have any charge. Means the oxygen of phenoxide ion will have high eager to donate electrons in the benzene ring. That's why the benzene ring of phenoxide ion is highly activated. Benzene ring of phenoxide ion is highly activated as compared to the benzene ring of phenol. Again, I am repeating, what is the reason? Okay, first, activated for what? Highly activated for electrophilic attack. As you know, electrophiles are attacking on a benzene ring for the electrons. And in the benzene ring of phenoxide, we have high electronic density. So that's why this benzene ring is highly activated for the attack of an electrophile as compared to phenol. Now why? Again, I'm repeating. Because in benzene ring, electron density is increased due to oxygen. The oxygen was delivering lone pair. That's why this resonance was occurring here, and electron density is increased on ortho and para position during resonance. But phenolic oxygen, after donation of electron, is getting positive charge, unstable. So that's why this oxygen will little bit hesitate to donate its electron in the benzene ring, because after donation, what it is getting? Positive charge, instability. That's why the electronic density in the benzene ring will be quite less. Oxygen is donating electron, no problem. But obviously after donation of electron, it is facing a problem. What problem? Positively charged, instability. So it will hesitate to donate electrons in the benzene ring. Whereas in phenoxide ion, the oxygen which is attached to benzene ring is already unstable. So it will not hesitate to donate electrons in the benzene ring, because after donation of electrons in the benzene ring, it is getting stability. That's why this benzene ring will have higher electronic density as compared to the benzene ring of the phenol, because its oxygen is eager to deliver electrons in the benzene ring, because after deliver of electrons in the benzene ring, the oxygen is getting stability. That's why this ring will have high electron density. That's why the phenoxide benzene ring will be preferred by electrophiles to attack on it. It is written there, benzene ring of phenoxide ion is highly activated for electrophilic attack. This is the main point in this concept. Now, when we are reacting phenol in the presence of water, and when we are reacting phenol in the presence of carbon disulfide, actually what is happening, because water is a polar solvent, so in water, phenol particles will dissociate to give us this phenoxide ion and hydronium ions. Means in water, phenol particles will convert itself to phenoxide ion. But CS2, carbon disulfide, or CCl4, carbon tetrachloride, they are non-polar solvents. Non-polar means they don't have negative and positive fields around them. That's why they can't dissociate phenol. into phenoxide ion and H positive ion like water was doing. So phenol will remain in this form. In this form. This is the important point. This is the main point. In phenol, in water, phenol is converting itself to phenoxide ion because water is polar. As you know, what are polar molecules? In 11th class, we have discussed them. They have a negative and positive fields around them, due to which they are able to break phenol into these two ions. But whereas these solvents are non-polar, they will not break phenol into phenoxide or H positive ion. Phenol will remain phenol like this. So, as right now we have discussed, the benzene ring of phenoxide is much more activated. So what is happening? All the three positions will simultaneously be attacked by bromine ions. Mechanism in next video we will discuss, because this ring is highly activated. Highly activated toward what? Towards electrophilic attack. And who will be electrophile here? Obviously brominium ion, because we have to react phenol with bromine. Brominium ion is an electrophile here. Now because the ring is highly activated, and obviously which positions? Ortho and para. Due to highly activation of the benzene ring, at one time all the three positions can be occupied. Three brominium ions can simultaneously attack on these three positions, and we can get tri-substituted product. Like this. Whereas this phenol, right now we have discussed, the benzene ring is not so activated. So at one time only one bromine will attack on it, and mono-substituted product we will get. One time ortho, and if another particle is there of the phenol, one time para separately. This is the reason. That's why. Now you will think that this was phenoxide ion, so O negative is there. Then finally how it will turns to phenol itself. In mechanism I will tell you how it will turns to phenol itself. H will come here. O negative will not remain like this. H will be joined on it. In mechanism I will tell. So this is the reason that why when phenol reacts with bromine in the presence of water as a solvent, we are getting tri-substituted product. And when phenol reacts with bromine in the presence of CS2 and CCl4, we are getting only ortho and para-substituted product. Because in water, the phenol is turning into phenoxide ion. And phenoxide ion benzene ring is highly activated by the donation of electrons from the oxygen. So that's why at one time, three bromine can simultaneously attack on it. So we are getting tri-substituted product. Whereas phenolic benzene ring is not so activated. So at one time, only one electrophile will attack on it, and we are getting separate products, ortho separate, para separate. And why they are not so activated, already discussed in the resonance of the molecules. That's it. Now in next video, we will check the mechanism part of this reaction. Thank you very much for watching the video.